All right, so today we're just going to talk about what nonlinearity is and how it changes vibrating structures. And so kind of the first thing that we want to talk about is the key difference between nonlinear systems and linear systems. And well, there are a lot of key differences, but I'm just going to list a few here. So the first and kind of the most important is that the principle of superposition doesn't hold anymore. So, you can't just apply, if you apply one force to a nonlinear structure and a second force, you can't just break those forces up and study them separately and then add them back later. That just simply doesn't work. The other thing that pops up from this is that if you've hopefully taken some vibrations class, we can't do any kind of modal decomposition. Sometimes you can, but towards week 7-ish, we will show when that actually nonlinear systems have, when you do something like that, you'll find that a nonlinear system will have more modes of vibration than it has degrees of freedom. So that's not something you can typically do. What else? We'll also find that multiple solutions can exist. And we'll add here for the same conditions. So a key thing about linear systems that have a solution, let's say we're thinking about equations of motion and having a solution to those differential equations, is that those solutions will tend to be unique. And so you'll have only one solution at a time, or for a given set of conditions, whether that's a forcing condition or some initial condition. For nonlinear systems, you can have multiple solutions, so uniqueness is not a thing anymore. And we'll see this in the next 2 weeks. We'll see when this pops up. All right, so another kind of important thing that I'll add here is that natural frequencies, they tend to change with amplitude. Or more naturally, they tend to change with the energy in the system. And when we get to, like, again, week 7 and we start dealing with nonlinear normal modes, we'll see how these are better depicted as functions of energy. That being said, has everyone here taken a vibrations class, like basic vibrations? Okay, I'll get you some, you send me a message on Discord, I'll get you some videos. If you haven't taken a vibrations class, both single and multi-degree of freedom, just let me know and I'll get you some YouTube videos that I've recorded that you can watch to kind of get a basic idea of what we're talking about. All right. So there is this inherent dependence on inherent dependence on amplitude in terms of frequencies. So the frequencies change with respect to the amplitude of the system. And if that amplitude is changing over time, like due to some decay, let's say, then the frequencies are going to change as well. Okay, we're going to add here just kind of a broad statement that some phenomena phenomena arise that have no linear counterparts. And what that means is that you cannot use linear tools or linear systems to try and study this type of phenomena. You have to use techniques for nonlinear systems. So basically everything you might have learned in a linear vibrations class cannot be applied here anymore, except for kind of ideas about modes, but even the thing like a mode is not really well defined in nonlinearity. Okay. And I would also add one more thing, that nonlinearity tends to scatter energy across the frequency domain. And we'll come back to that last one throughout the class. So nonlinearity tends to scatter energy across the frequency domain. Okay, so one more thing I want to add just about the notes. Here I've kind of typed portions of it. Moving forward, I won't be typing because it just takes a lot of time. So if there's ever anything that I've written either in class or just on the notes that you can't read, just tell me and I will explain what it is and then fix it on my iPad and then upload a new copy. Okay. Can everybody read what I've written up here? Okay. All right, so in general, engineering is just based on linear theory. Everything you learn as an undergraduate is based on linear theory. Even as a graduate student, you're primarily focused on linear theory. And everything done, almost everything done in industry is based on linear theory. The reality is that we live in a nonlinear world, and every system is nonlinear. Some behave linear under the right conditions, and linear can be a good model for them, but they're still nonlinear no matter what. And the comparison that mathematicians will make is like saying, like linear systems are like bananas, and nonlinear systems is like everything else. So there's only a few bananas in the world, and there's a lot of everything else in the universe. And that's where we're at. So some sources of nonlinearity, and we're going to go through some of these in greater detail. Primarily, we're going to focus on mechanical examples in this lecture, but there are examples from like fluid dynamics. Obviously, the Navier-Stokes equations are nonlinear, equations from electromagnetics as well, and so forth. But we're going to focus on mechanical structures. All right, so in kinematics, a common source of nonlinearity is just from the Coriolis acceleration. For constitutive relationships, we can think about just nonlinear stress-strain relationships. That might include plasticity, but it also may not be a plastic response. It may just be nonlinear in an elastic region. A lot of boundary conditions lead to nonlinearity, although boundary conditions themselves don't really exist as we model them. But nevertheless, we can say things like vibro impacts, which is the strongest type of nonlinearity. Clearances are by far the most common source of nonlinearity, and I believe we'll talk about clearances at some point in this lecture. Well, if not, we'll talk about it at some point. Any kind of loose connection as well. Free surfaces in fluids can introduce nonlinearities as well. Things like nonlinear body forces, these tend to arise in electric and magnetic systems. And what we're primarily going to focus on, although the techniques we develop will be applicable to all kinds of nonlinearities, but we're mostly going to focus on geometric nonlinearities. And these arise from large deformations, or geometry, quite simply. All right. So, first example we're going to look at is a beam with a geometric nonlinearity. Here we're considering nonlinear stretching of the neutral axis of this beam. And we're still assuming that kind of the slopes and the deflections are small with respect to the length of this beam, but they're large enough to allow this deformation of that neutral axis. Okay, so here we have, well, U is the deformation of that neutral axis being stretched in the horizontal direction, and then V is a vertical deformation of this beam. S is arc length throughout this. Okay, so we're making some assumptions here. A uniform cross-section, there's negligible shear deformations at this point, and we've also asserted the Bernoulli assumption. And then from there, what we can do is we can solve for this arc length ds of this differential element here of length dx. And what we'll find is that ds is equal to the quantity dx squared plus dv squared times, or raised to the 1/2 power. We can then pull out a dx from this, and we'll get 1 plus the quantity dv dx squared raised to the 1/2. We're then going to expand that using a Taylor series, or you could use a binomial expansion as well. Just expanding that, we're going to get that ds is equal to dx times 1 plus 1/2 dv dx squared plus some other terms that we're going to not write out for right now. So the Taylor series, so it's an infinite series of terms, and we've only kept here the first term, that squared term. So from there we can define the stretching of that differential element during that vibration, and it's going to be dl is equal to ds minus dx, and that's equal to 1/2 dv over dx, that quantity squared plus all of those other higher order terms that we have written here. And then the change in length across that whole beam is going to be equal to delta L, which is equal to 1/2 times the integral from 0 to L of dv dx squared dx, and again, plus higher order terms that we're leaving out for right now. Okay, so we're now going to assume that the constitutive law of the material is linear, and that tells us that the stress, or sigma, must be equal to the elastic modulus, big E, times the strain, or epsilon, which in this case we'll just define as a simple strain being the change in length divided by the original length. We'll also recognize that the stress is equal to the normal force along the neutral axis divided by the cross-sectional area A. And from there we'll find that N over A is equal to E delta L over L. And then substituting in from above, we will find that that normal force N is equal to EA over 2L times the integral from 0 to L of dv dx squared dx plus higher order terms. From here, we're going to do a force balance. In this diagram, I've taken a differential element, and I've just done a free body diagram, basically. With the shear forces, the moments, and that normal force due to the stretching of that neutral axis. From here, we're just going to break it up into x and y components, just like you would do for any other kind of system. And then from those, we're going to end up deriving the governing equation of motion. So starting with in the x direction, we will just have here n times the cosine theta minus q times the sine of theta. That's equal to 0. In the y direction, now we're going to switch to using partial derivatives. So just as an aside, something like v dt, this is equal to the second partial derivative of v with respect to t. So we use subscripts for partial derivatives, basically. So we're going to get rho times v dt, and that's going to be equal to partial over partial x. And we have skipped some steps here in terms of switching from total derivatives in n to partial derivatives. We've just skipped some steps in terms of time. However, that n, the total derivative there should just be partials if we weren't to skip these steps. Nevertheless, we continue. All right, so we have partial over partial x times n sine theta minus q. This should be q cosine theta. In my notes, I have a sign here. And that is it for the balance of forces. For the moments, we will get m sub x, so that is the partial derivative of m with respect to x, minus the quantity q times the cosine theta plus n sine theta multiplied by 1 plus v sub x plus n cosine theta minus q sine theta, and that's equal to 0, and that is our balance of moments. Okay, so from here we combine these equations, and I'm going to skip all the steps and just give us the final equation. What we end up with is rho times VTT is equal to minus EI V sub xx. That's our underlying linear equation, which is a fourth order partial differential equation. It's known as the beam equation for an Euler-Bernoulli beam. And then the second term over here, we're going to have quantity EA over 2L times the integral 0 to L of V sub x squared dx. That is multiplied then by Vxx. So we have nonlinearity here, both in the sense that this Vx term is squared, but it's also multiplied by Vxx as well. Okay, any questions on this?
Yeah. So how is this stays nonlinear when we can just do the integration for the Vx? Because as long as we have integration and different integrations, just going to turn into a constant.
Depends on what the function of v is. Depends on what v is, right?
I don't see it. Because V dx can be just integrated, even if it's numerically. Just going to return a constant.
It can be a function of time also.
Even if it's a function of time. Like we're talking here about the x.
So yeah, again, he's right. That's a good point. So even if we can integrate that, it's not going to be some constant because it depends on time as well. So it might be a constant for that v for the like displacement wise. Well, it won't be because it's some function.
But it will be a like if we deal with it like with respect to like separate them, then we're going to have some
Separate what?
oh,
Time and space.
yes.
So that is not a valid approach. That's the problem.
Oh,
Now, I would agree with you
yes.
that if we could do that, it works. So that goes back to the superposition doesn't hold. But I agree with you. If we could do that, then yes. Then this wouldn't matter. All right. Other questions? Okay. Let's take another look at a second example. This is just a particle or some mass that is connected by some thin wires to ground, and it is displaced transversely, shown like here. And this is a geometric nonlinearity that arises just due to geometry, quite literally. Okay, so in this case, the restoring force is going to be, and again, I'm skipping steps here. You would have probably done some type of Newtonian analysis on this, or you could have done a Lagrangian analysis, but nevertheless, we're just skipping that. The restoring force is K times X, that's just our linear force. Then it's multiplied by 1 minus L divided by the square root of L squared plus X squared. This comes from Pythagorean theorem, and we've just skipped some steps to tell you the truth. What we're going to do is a Taylor series expansion for about x equals 0, which is the equilibrium point. We're going to do that expansion we're going to actually just look at the bottom term, this term right here. Not the numerator, the denominator of that. We're just going to do the expansion there, and then we'll come back and plug it in a moment. So we have L squared plus X squared to the 1/2 minus 1/2. So we're doing Taylor series. You can also do what's known as a binomial expansion. They tend to be the same actually in terms of the results you get, but either of these will work. So the first term we're going to have is 1 over L minus X squared over 2L cubed plus 3x to the 4th over 8L to the 5th plus an order 6 term. This big O means that of all of the terms that are in there, there are at least as big as 6 in this case. Yeah, because we only have even ones here. What we're going to do here then is to neglect those higher order terms, and we will get 1 over 2L squared times KX cubed, which we can relate to the wires as being EA over L cubed X cubed. So one thing I want to point out here is when we started up here, we had a 1 right here, which meant that we had a linear term in there. We had this kx term. When we did this expansion, we ended up losing that term, that kx term, it would have been this 1L right here, which if we were to substitute back up here, we would get L over L, and then you would have 1 minus 1. And so we actually end up losing that linear term. And so this is what we would call an essential nonlinearity, and that means that it has no linear component in the sense that it only has nonlinear components. Okay. All right. So now if the wire is preloaded, then you get some initial tension in there, and then you do get a linear term. So in my group, we do experiments where we use wires for nonlinearities, and we end up having to clamp them down, which creates some type of tension in them, and so we always have a linear component. If you were able to realize this without having that initial tension, you would get a pure nonlinearity. And it's not just an x cubed term, there is an infinite number of these, but usually we truncate this and just look at the x cubed, or some polynomial. Here's some examples of additional springs that people have designed or studied. There's many of these ones. The picture on the far right is kind of hard to see there, but it's a pair of buckled beams, actually, with a mass in the center. If you're interested, I suggest you check the references. All right, any questions on that application or example? Okay, in that case, we're going to consider just a simple pendulum. This is a common system studied in linear dynamics and linear vibrations as well. We're going to consider the following assumptions: that the rod shown here is massless, there's no deformations in that rod, there's no damping, air resistance, friction, external forcing, except for gravity. It's only external force. And it's in plane motion, so it's only a single degree of freedom in terms of polar coordinates. And then the rod and the mass are rigid. So perfect, simple pendulum. Okay, so we're just going to directly write out what the equation of motion is. Generally in this class, you won't be asked to find equations of motion. You will typically be given one because we're more interested in studying their behavior. And there's enough work in that to warrant not having to derive these equations anyway. So we're just going to typically jump ahead. So anyway, the equation of motion is theta double dot, which is a time derivative, second time derivative, plus omega 0 squared times the sine of theta, and that's equal to 0. And here omega 0 squared is equal to g divided by L. Okay, and so right here the nonlinearity arises in this sine of theta term. In a linear vibrations class, you will typically assume small motions, and then you will linearize that sine term and get back just the theta instead. Here we're going to not do that. We're going to consider large amplitude motions. And what we can then do is expand the sine term into an infinite series. That becomes theta minus theta cubed over 3 factorial plus so on. And then you can write this out as an infinite series from n equals 0 to infinity of the fraction minus 1 raised to the n, theta to the 2n plus 1 divided by 2n plus 1 factorial. So in linear vibrations, we will truncate this series and keep only the theta term right there. In nonlinear dynamics vibrations, we could keep as many terms as we want. Usually we will just truncate and keep the cubic term. And that it turns out to be interesting and rich enough that we can do a lot with that. Okay. All right, so what we're going to do here is we're going to multiply that equation of motion by theta dot, and then we're going to integrate with respect to time, or t in this case. So I'll just write it out. Well, theta dot times theta double dot plus omega 0 squared theta dot times the sine of theta We then integrate those, and we'll have theta dot times theta double dot dt plus omega 0 squared times the integral sine of theta. And we'll write that theta dot there is d theta dt. Then we have another dt there. We'll come back to that second integral in a moment. On the other side, we're integrating 0. Oh, I left that out. 0 dt, and that just becomes a constant, which we'll call e. Okay, so going back to that middle integral, we can eliminate the dt's, and then we get the integral of sine theta d theta, which is just minus cosine theta. So from there, what we get then is, oh, and by the way, that first integral evaluates to being, oh, we're missing a dt there. T there, and it evaluates to being just 1/2 theta dot squared. So we get 1/2 theta dot squared minus omega 0 squared times the cosine of theta, and that's equal to e. And this is known as the first integral of motion. And in this case, it's the conservation of energy, but first integrals of motion are not always conservation of energy. They're often conservation of energy, but not always. Okay. All right, any questions on what we've done so far? All right. So in that case, let's just take a brief aside and talk about, I said that uniqueness of solutions goes away with nonlinear systems, but existence also goes away. So a lot of systems that are nonlinear just do not have solutions, period. And so basically, we just derived what's known as the first integral of motion for this, and then for any n degree of freedom system, there must be 2n minus 1 integrals of motion. If a solution exists, there's actually 2n. One of those you can usually throw away, and you can show it's equal to time. But there must be 2n minus 1 integrals of motion for an analytical solution to exist. And in such cases, we call that an integral system, integrable system. So all linear systems are integrable, and few nonlinear systems are integrable. And so a common example is a system that supports chaotic motions, and we'll come and talk about what chaos is at some point. But any system that is chaotic is not integrable, and it has no analytical solutions, so you cannot predict analytically what the system will do. You can still make numerical predictions, but they're never going to be perfect, and they're going to always be very sensitive on initial conditions. Anyway, for our pendulum, it does have the right amount of or integrals of motion, and it does have solutions actually. Okay, we'll come back and we'll see this pop up later on as well in the class. All right, so this first integral of motion gives us two things. The first is the ability to compute the solution phi, or theta of t, and the second is the ability to compute what's known as a phase portrait, and we're going to have, our second lecture is going to focus on phase portraits and phase space. For now, we're going to focus on how to compute a solution, and it's not going to be a pretty solution, but it's still a solution, is my point. Okay, so we're going to basically solve for theta dot. So we have 1/2 theta dot squared, and this will then be equal to e plus omega 0 squared cosine theta, which we can then write and break this up. Oh, that should be theta dot squared. We can then write d theta dt is equal to plus or minus the square root of 2 times e plus omega 0 squared cosine theta I'm just going to reposition this. And then from here, what we have is now the angular velocity equal to a function of the angular displacement, and we could then compute what's known as the phase portrait. We'll come back to this at some point, either later today or on Thursday. What we're then going to do is separate these out, and we will end up with plus or minus d theta divided by the square root of 2 times e plus omega 0 squared cosine theta. This is then equal to dt. And from there, we can solve by integrating with respect to time or with respect to theta, and we'll find that t is equal to the integral of 1 over the square root of 2 times e plus omega 0 squared cosine theta d theta plus k, some constant k. And that integral is known as a Jacobi elliptic integral. And basically, what it allows us to do, well, if we can solve that integral, we can then solve for theta, effectively. Maybe. Okay, but what do we really get from this solution? From this kind of solution, we're able to find an oscillation in time or in theta from some initial condition to the minus, theta 0 here is an amplitude, and this system is going to oscillate from theta 0 to minus theta 0 because it's conservative. And theta 0 is something we would get from initial conditions because it's unforced. And then from there, what we can say, and somehow be able to solve, is that there's an oscillation from, again, theta 0 to minus theta 0. Okay. So, kind of an aside, I'll say here, is that for the damped pendulum, solution does exist. People have shown that there are the right number of integrals of motion, but nobody has discovered what that is yet. So we know a solution exists, but we don't know what it is. Either we haven't discovered it, or you might say that we haven't invented the right functions yet. I tend to believe it's more of a discovery than an invention, but there's a debate there that's not in this class. Okay, and then if we take a look at a damped and forced pendulum, this system actually has no solution. And it's because it's chaotic, and there's a C missing right there. So this system is chaotic, and no solution exists to it. So you cannot solve it analytically. You have no hope of ever being able to solve it analytically. And even if you simulate its response with the same initial conditions and the same forcing on two different computers, you're going to get two slightly different answers. And if you change those initial conditions, then you can get drastically different solutions. And Mohammed, I know you know all about this. So anyway, are there any questions about what we've gone through today so far?
So when you're saying here that the solution doesn't exist, you're just talking about analytical solution.
So here you can show that it does not exist. Oh, oops.
No, I'm not in the case about chaotic.
Oh, no, yeah.
Okay.
So the one above, yeah, we know it exists. We just haven't been able to determine what it is yet.